Good morning, sirs and ma'ams. Good morning, sirs.
Good morning, sir.
Okay, well done. Okay, welcome back. So let's see how much we can go today. I will still continue on our series of screen film and system. We did the introduction the last time we met. So today we are going to develop it further. Basically today we'll be looking at the screen film system. Of course, we know that the film is always inside the screen. Of course, enveloped with the cassette. And the film, of course, is not supposed to be exposed. If you bring it out, it has become exposed. You wouldn't be able to use it again for a radiography. And like we know, the film uses negative recording, different from a normal photography that uses positive recording. For example, if you take a snapshot, um, you're going to have shades of very so many shades. Let's say you're using a black and white system. You're going to have shades based on the amount of lights that the camera captures from one's body, reflection from one's body. Assuming you have an empty film, you just take a snapshot of it. You're going to have a black background. But for film, but for the radiography film, it is the reverse is the case. So we are going to look at start with some examples of screens. We have so many types of film that have developed. That have gone through so many processes, through some developmental stages. At some point in time, there had to be some changes from one film type to the other. And depending on the radiography or depending on the imaging modality we are using, we might need to require one type of film, one type of screen or the other. By screen, as we introduced last time, by screen, we just mean the light sensitive part of the system, of the screen film system. The one that emits that is in which X-ray falls on the film, and then from there, light is emitted. Of course, we can screens actually phosphor. So we have a lot of them from the old calcium tungstate. It was there for a very, very long time until the advent of some of rare earths and phosphorus. It has an efficiency, absorption efficiency of about 5%. So when gadolinium or sulfate came into the foray, it replaced it, of course, quickly because it had better efficiency. And from there, we can also have cesium iodide. This one is very, very hygroscopic. Sorry, it doesn't work in a moisture environment. It doesn't want the moisture. Moisture can actually destroy it. So therefore, we cannot use it in screen film system because in screen film system, we're actually dealing with, want to develop the film. The film has to be developed inside liquid, which of course are made up of water. So system is not used in ordinary screen film and radiography. You can use it in say a fluoroscopy, Basically, it is the major phosphor used in the nuclear medicine aspect and camera. So system side, sorry. Iodide is also an example of a phosphor, but it's not used in general radiography. Then we have yttrium. Um, we have yttrium, tantalate, which is double T. Now, the yttrium tantalate is also a very, very good by phosphor used in some of our screen film system. All of the, of course, but it is not so much unpopular. Of course, through research, um, so many things have gone into research to come to the conclusion that, or to come to the moment where we are, in which we use gadolinium oxysulfate. So this is also an example of a phosphor. Then we also have this tantalum. We also have lanthanum oxybromide. Oxybromide. It's also an example of one of the screens that we have. Lanthanum oxybromide. Then the one we use, the most popular of them all, we're going to be comparing it side by side with calcium tungstate. Gadolinium gadolinium oxysulfide. Gadolinium oxy. So these are the two major ones we'll be considering. We'll be looking side by side. Gadolinium oxysulfide. This is what I did chemistry. Well, just for us to, at times you might, they might need us to mention the name and the chemical formula, but it's really not necessary. So these are the five main types of screens that we use in our screen film system. But these two are the most popular ones. But today, what we use is the gadolinium oxysulfide because of its high conversion efficiency of about 50%. This one has a 5% conversion rate. So from there, we're going to continue. I'm going to look at the function of screen. Look at the function. Like we did say in our last lecture, film itself is so film itself has an excellent what's called resolution, spatial resolution. So why do we bother adding film to the composition? I mean, why do we make it a screen film system like we did say in the last lecture? Just because film is not it's not a very good what's it called, material for absorption of an X-ray. If you want to make it, if you need to have an optical density of say 1, then of course you need to use so much radiation that of course will become an issue when it comes to radiation and protection. So that is why we need to put in screen, because these screens are actually phosphors that increase the conversion of that converts light and also intensifies the amount of light and form. So screen has two functions. It does. It absorbs an X-ray and now emits light. That emits visible. That emits a visible light. Because actually it is the light that affects the film. The film is usually sensitive, much more sensitive to light. Hello? Dr. Ekwe. Dr. Ekwe, do you have anything to say? I thought you wanted to ask a question. Hello? Am I communicating? Hello?
Yes, sir.
Okay. I thought you wanted to ask a question. So the functions of the screen are just of a screen are twofold. The functions are twofold: absorb the X-ray and then it's visible light. Whereas if had been an ordinary film system without a screen, this one will just act on the X-ray. X-ray will just follow it, but it has a very poor propensity for X-ray. If film had a very good amount of a conversion efficiency for film or absorption efficiency for X-ray, there wouldn't be need to bring in X-ray into the system. But just because of it has a very poor affinity for X-ray, so that is why it is not used. But whereas it has a very good affinity for light, and that affinity um, is produced. That light is produced by the screen. So let's see how much we can rush today. So we have there are so many things to consider. We consider why them looking at them, while looking at the screen. How do X-rays? How do the screen convert? Of course, they convert the X-ray that fall on them. How the X-ray photons that fall on the screen, and so on and so forth. So we have two main efficiencies. We want to look at how the screen performs. Efficiency characteristics. Efficiency characteristics of the film, we can broadly say that conversion efficiency, and absorption efficiency. So these are the two main efficiencies we talk about, we look at when we want to look at the characteristics of film. How much is the screen, sorry, not film, how much is the screen? But anyway, we talk about the two at the same time because we're looking at the conversion. It's a kind of twofold and stuff. It is based on both the screen and the film. How much of the X-ray the screen is able to convert to light, and how much of the light is used to affect the film to produce a particular optical density. So conversion is the amount of X-ray photons that the screen is able to convert. Whereas absorption is the amount of X-ray photon. Okay, let me start with absorption. I think that should be the best way to start. Absorption is actually the amount of X-ray photons the screen is able to absorb. The amount of X-ray photon the screen is able to absorb. And this is at times referred to quantum detection efficiency, QDE, quantum detection efficiency. It is the amount of X-ray photons that the screen is able to absorb. And there are some factors that actually determine this QDE. The thicker the film, the thicker the screen, the better the QDE. So if you have a thicker screen, you're going to have a much more higher absorption efficiency because you have a small screen, the amount of X-ray falling on it will not be the same thing as a thickened screen. This one, so the size matters when it comes to absorption efficiency. The bigger the screen, the bigger the absorption efficiency, and the bigger the QDE. A graph has been, we have a graph to explain that. Let me quickly share that with us. But before then, I was rushing. It is good if we look at the structure of the screen. Let's quickly look at the structure of the screen before we look at the relationship between thickness of the screen and the quantum detection efficiency. So let's quickly look at the I hope you can see that. I hope you can see that.
Yes, sir.
Okay. So this is actually the screen film system. Of course, the whole arrangement is inside the cassette, which of course we normally see the radiographers move from the X-ray room to the dark room, or from the dark room up to the X-ray room. So we have the top port. Of course, this is the cassette holder, top of the cassette holder. Then, most times, for general radiography, we normally have an emotion that is sandwiched between two screens. Yeah, you have the first screen, specified screen, and this is the first one, this is the second one. Then you now have a film sandwiched between them. Of course, this is the emotion, which is actually the silver halide that is that will be affected by the light. So as light, as X-ray comes, or X-rays come down here, they are affected, they interact with the screen. After interaction with the screen, of course, light, you have emission of light, which will now affect this emotion here. Of course, we have the T grain. This is just an electron micrograph of the T grains on top of the film. The grains of the intensifying. So this is just a rough sketch of what we have. That tiny film that we have is actually made up of so many layers of the material. So let me start another share. This time I want to look at the absorption efficiency of the film based on their based on their thicknesses. We have to show you. Okay. So we have that for so many screens. For so many screens. We have the general trend is the more the thickness, the better the quantum detection efficiency. Now, of course, it's a measure of the absorption efficiency of the screen. You have for calcium tungstate, for yttrium tantalate, then for gadolinium oxysulfide. But this is the preferred choice. You can always see that each particular thickness, the gadolinium oxysulfide then offers a better quantum detection efficiency. So no matter the type of film, the bigger the screen, the thicker the screen, the better the absorption efficiency, which of course has um, something to do with the overall efficiency of the screen film system. Then for conversion efficiency, there are so many things you look at. You stop the share. For conversion efficiency, there are so many factors that determine the conversion efficiency. For calcium tungstate, it's just about 5%. The measure to be around the 5% calcium tungstate is just around the 5% conversion efficiency. But for gadolinium oxysulfide, it is 15%. So it is just times 300% increase from calcium and tungstate. Of course, that is why this one has over. Gadolinium oxysulfide has taken calcium tungstate as a choice, as the right choice for a screen film system. Like I was saying, conversion efficiency has got to do with so many factors. It doesn't depend so much depend on the thickness of the screen, but it depends on so many things. The inherent property of the screen itself. It also depends on how much film, because we can't just say the combine. We can't rate. We can't measure conversion efficiency of the screen alone. It has to be in combination with the screen. With the emotion. So the amount of light after the screen has affected the X-ray, and we have so many light photons emitted. The amount of light photons that will then affect the film to give a particular optical density. All of these are what we use to characterize the conversion efficiency of the screen film. But the thing is this: for this and two screen, calcium tungstate and oxysulfide, this one is better. It's been proven to be better. So it has taken the place of calcium and tungstate. So we have for screens, there's also something we need to know about them screen. We don't just use screen out of the blue. We have a reason for using one screen in a particular radiography to another modality. In a particular modality to another modality. For example, in general radiography, we normally use two doubled screen like we have here. Like I did show before. For general radiography, the normal thing is to use a screen. A screen film system that has two screens sandwiched between you have two emotion layers. Then you now have the film. The film in between. So you can actually turn it upside down and you just perform the same function. So that's a whole reason for that. Then in some radiography, in some modality like mammography, we don't use a double screen. We use a single screen for reasons that we will get to know very soon. So for screens, we can also screens can either be double or a single. For double, we usually use we normally use this for general radiography, whereas for mammography, in which wants a very, very good detail, then we use a single emotion, single screen system. So let me quickly use share the screen to further explain that why we need to use single screen for some system, for some modality, and a double screen for some. Okay. Even before then, I think I need to explain this. We have the distinction between a thick and a thin screen. What's what's what will be the effect of changing the screen from a thick one to a thin one, and from a thin one to a thick one, even before we go to double and then single screen and system. If we look at the double, I mean this and thick screen, we have one of the advantage of having a thick screen, like we did say before, is to increase the quantum detection efficiency. But it also comes at a disadvantage. It also comes at a cost. And the cost is you're going to have the light photons will, of course, immediately they are produced here. Light photons are produced, and they begin to disperse in so many directions. You can see the light, they begin to disperse isotropically in all the directions. So at the end of the day, we are going to have much more lateral dispersion of light in this thick screen, because it's going to travel a further distance. It's going to travel much further distance than here. In here, because it is thinner, because the screen is thinner, there won't even be so much lateral dispersion of light here. Because here, as it is, because some photons will travel down before interacting with the phosphor. I mean, some X-ray photons. Whereas so in all the cases, generally, the photons, the X-ray photons, more X-ray photons will diffuse down into the stuff before interacting. Apart from that, too, the light that after the light has been produced, they begin to disperse in so many directions. So that is going to also affect the spatial resolution of the screen film system. So the one that has a thicker screen film system has a poorer lateral resolution. You can see this screen. At the end of the day, this is the line spread and function of the screen film system. You're going to have look at it. This constitutes a very, very poor spatial resolution. But for this, you have a thin screen, not going to have so much lateral dispersion of light. At the end of the day, we have a line spread, function of that represents a good geometry. So let me see if I have a diagram that helps us explain double and the single emotion. Okay, we don't have that. We don't have that there. Oh, no problem. For double emotion, for double screen, double emotion, Let me just take this up on screen. This is the top screen. This is the top screen. 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 This is a top emotion and the down emotion. So the screen, the theme is now sandwiched between the. So this is for double screen, double screen, double emotion system, which we use in normal radiography. Then for the one in mammography, configuration is this way. Just one, just have them one. This is the screen. This is the screen. You can see the orientation. This is the emotion. This is the, and we can just see the orientation. In the general radiography, we have our theme. We have the X-ray coming down this way, affecting the screen. Interacting with the screen. We now have the light producing them, blah blah blah, forward direction, and it affects this. It is possible for some exophotons to not interact with this, or when they get here, they can also interact and produce light photon. The light photon, of course, will travel in so many directions. The one traveling up will be the one that will affect the emotion that the film emotion that we have here. The film and the emotion, of course, they are just one compact one system. So we have that. But for mammography, in mammography, we need a very, very high grade film screen system. Not just high grade. We need them to have one screen and one emotion layer. And the configuration, the configuration is the screen is placed down, while the emotion part is placed up, not this other way around. Why? Because as light, if you have it this way, assuming this is our screen, assuming this is our screen and this is some light will okay, let me explain this first. We have to have it this way because the X-ray photon, as they are coming and then interact with this screen, most of the X-ray photons will interact at the top here, at the junction between the emotion and the screen, and light will be given off. Light will be emitted. So the light will be emitted will immediately affect the film here. Most of the X-ray photons will interact at this junction. So there wouldn't be so much dispersion of the light. The lateral dispersion of light. Most of them. So the detail of whatever we want to see is preserved. But if you now take it this other way, of course, we can't compare these two in terms of because there wouldn't be lateral dispersion of light here, or very, very minimal lateral dispersion of light. But for here, we're going to have them. But we need this system in X-ray, in general radiography, because we need as many light and photons as possible to give a very, very good a radiograph of quality of a good optical density. But yeah, our main concern is because of course in mammography, what we are looking at, what we want to see is if we have some some tumor, whatever, inside the breast tissue, and of course, these stuffs, the microcalcification, blah blah blah, and so on. They have a very, very similar contrast and properties. So it is good for us to have a very, very good system that will be able to distinguish between these abnormality. So therefore, and that is heightened, is helped with this arrangement, this configuration. If we had had it up, I mean, if this one had been our screen, if this one had been our screen, if this one had been our screen and not our emotion, let's just imagine the screen, turning it upside down. This one being our screen and this one being our team emotion. So this will help get another one. Assuming we have this as our theme and this as screen. Immediately the exoprotons land here. Most of them will interact at this surface,